Hello everyone. My name is Prashant Pal, a machine learning intern at Mentornis. This video presentation focuses on predictive modeling for disease diagnosis. Healthcare professionals face challenges in timely disease diagnosis due to complex health conditions and the need for precise biomarker assessments. Our datasets include diverse health attributes like cholesterol levels, blood cell counts, hormonal markers, and more, alongside disease diagnosis information. Our goal is to develop a predictive model that accurately categorizes individuals into diseased or non-diseased groups based on their health attributes. This model aims to enable early disease detection, effective patient management, and improve healthcare outcomes while reducing costs and enhancing overall patient care quality. Let's talk about the data collection process. We have access to two comprehensive datasets, train.csv and test.csv, provided by Mentornis. These datasets contain diverse health attributes along with corresponding disease diagnosis information, which are essential for developing predictive models for disease diagnosis. We import various libraries such as Pandas, NumPy, scikit-learn, matplotlib, seaborn, and plotly.express for different tasks. Moving on to data preprocessing. All variables in the dataset have been converted to lowercase strings for consistency and ease of use. Additionally, both the train.csv and test.csv datasets have no null values, indicating complete data with no need for imputation. Furthermore, all data points are already scaled between 0 and 1, eliminating the need for additional feature scaling. Finally, the disease column, initially an object, is converted into float 64 using ordinal encoder to identify the best correlation features. Here we have created a bar diagram using plotly.express for visualization of a total of 2,351 participants. This bar graph showcases the distribution of individuals based on their health conditions. Starting with the healthy group, we see that 556 individuals reported no health issues. This is the second largest group among our participants. Next, we move to those diagnosed with diabetes, comprising 540 individuals. The thalassemia group follows closely with 509 participants affected by this genetic disorder. Anemia, a condition characterized by a lack of healthy red blood cells, affects 623 people, making it the largest group in our survey. Finally, we have the thromboc group, with 123 individuals dealing with low platelet counts. In this correlation heat map, we are able to quickly see how different features relate to each other. The colors indicate the strength of the relationship between each pair of features. What's interesting is that the top 5 correlations fall between 0.2 and 0.27. This suggests a weak to moderate correlation between these features. While it's not a very strong correlation, it's still worth noting because it could potentially affect the accuracy of our predictive models. Understanding these correlations helps us fine-tune our analysis and make more accurate predictions in the future. We've plotted a scatter matrix to visualize the relationships between the top 4 features that are correlated with disease: white blood cells, heart rate, glucose, and hematocrit. From the scatter plots, we can observe some patterns in how these features interact with each other and with the presence of disease. Like, we can see how changes in white blood cell count relate to variations in glucose levels or heart rate, which could provide insights into potential health indicators. Overall, this visualization offers a clearer picture of how these factors interplay with disease presence, aiding in understanding and potentially predicting health outcomes. Here, we've split our data from train.csv into xtrain, ytrain, and test.csv into xtest, ytest. By separating our data this way, we can train our model on one set, xtrain and ytrain, allowing it to learn patterns and relationships from the data. Then, we can test how well our model performs on unseen data using xtest while comparing its predictions to ytest. This division helps us evaluate how well our model generalizes to new, unseen data, ensuring its reliability and accuracy before using it in real-world applications. In this slide, we are exploring 5 popular machine learning models that help us make predictions based on the given data. First up, We have logistic regression, which is great for binary classification tasks. Then, there's the decision tree classifier, which makes decisions based on features to classify data into categories. Next, the random forest classifier is like a group of decision trees working together, voting on the most likely outcome, adding robustness to our predictions. The naive Bayes classifier uses probability theory to predict the category of a given data point, making it simple yet effective, especially with text classification tasks. Lastly, the support vector classifier creates decision boundaries to separate different categories, aiming to maximize the margin between them for better classification. By using these diverse models, we can explore different approaches to understand and predict patterns in our data, ultimately helping us make more informed decisions. For evaluating the performance of various machine learning models, we use different metrics like accuracy, F1 score, precision, and recall. These metrics help us understand how well our models are performing and which ones are most effective for our specific task. By comparing these scores, we can choose the best model for our needs. In conclusion, naive Bayes emerges as the best model overall based on the performance metrics. It has the highest accuracy, 0.5370, and recall, 0.5370, making it a strong candidate for predicting the likelihood of a disease. High recall is crucial in healthcare for minimizing false negatives, ensuring that individuals with the disease are correctly identified. Missing a true case of a disease, false negative, can have severe consequences, including delayed treatment and worsening of the patient's condition. As secondary considerations, SVM and hyper-tuned random forest show competitive performance, with relatively high precision values of 0.5128 and 0.5371 respectively. While false positives can cause stress and extra testing, they are generally less harmful than false negatives in healthcare scenarios. Thank you.